Okay, now let's take a look at another type of special case of a collision, one in which the objects bounce off of each other perfectly without losing any of their kinetic energy. We call this a perfectly elastic collision. So perfectly elastic, the two objects or the three objects or however many objects, all the objects hit each other and they bounce off perfectly, and none of the kinetic energy is changed forms to another thing. So this doesn't actually happen in real life. If you have two things that collide, they're at least going to produce a little bit of noise, right? And that would be some form of conversion from kinetic energy to some other one. But some things get very close, and so we can model some things as being perfectly elastic. So in this exercise, we have a 400-gram glider moving to the right, collides elastically with a 500-gram glider moving the opposite direction, so to the left. And we want to find the velocity of each one after the collision. So like any conservation of momentum problem, we need to set up a before and after. And since momentum is a vector, it's also very important that we have a coordinate system, right? So call positive x to the right, positive y upwards. And then let's look at what's going on before the collision. So before, we have a 400-gram glider right here that was moving to the right at 2 meters per second. And we had a 500-gram glider which was moving to the left at 3 meters per second. And this is what's going on before. And then after this collision, we have a 400-gram glider and we have a 500-gram glider moving a little bit differently, right? We don't actually know either of the velocities. We can assume, actually, let's just say we don't know. Let me actually call them, just for the sake of subscript, let's call this glider A and call this glider B. So this is A and B. And we don't really know what the velocity of A is in the final condition or the velocity of B is in the final condition. We might assume that, and it's probably a fairly safe assumption that one is going off to the right and one's going off to the left. So they hit and they bounce back the opposite direction. So if A was initially traveling to the right, then after it's going to be traveling to the left. That's a fairly safe assumption, but not always the case. Kind of depends also on how their masses are related too, right? So, if this one were 400 kilograms and this one were only 500 grams, then it's likely that they both would be moving off to the right because this one would be so massive, right? So it's not just, you can't always just assume that they're going to bounce back off of each other. They could actually both go in the same direction after. So let's take a look at what it is. Let me actually get rid of these directions here. So since the problem tells us that the collision is perfectly elastic, we know that the kinetic energy is conserved, and this results in this equation, if it's perfectly elastic, and it's generally, I would start out with this equation. We get to use conservation of kinetic energy as well as conservation of linear momentum for this problem. And the conservation of kinetic energy, which is what we get if it's elastic, this simplifies down to just the difference in the velocities after the collision. So VB final minus VA final is, actually I don't need those parentheses, VB final minus VA final is equal to negative of the difference in their velocities before the collision. So negative of VB initial minus VA initial. And these are all vector quantities as well. So the the difference in their velocities after the collision is negative of the difference in their velocities before the collision. And there's a lot of ways to write this out. Just make sure you have b minus a and then b minus a here, so you have consistency there. I think this is the easiest way to remember it. So we can plug in, we know some information about their initial velocities, right? And so we can plug this in, and we get here VB final minus VA final is equal to negative VB initial B, we called this one. So that, now it was moving at a magnitude of 3 meters per second, but based on my coordinate system, which we established here, so we have to be careful with our sign convention based on what we've established. This is negative 3, and VA initial is positive 2, right? So I'd say that's probably the most common mistake with perfectly elastic collision exercises, is the sign error here, because only the speed was given to us, right? We have to be careful to give it our sign. And so this was negative 3 minus a positive 2, right? And what this results in is we have VB final minus VA final is equal to negative 5, right? Oops, sorry, negative of, this is negative 5, and then we have a negative in front of that, so it's a positive 5, yes? And so what we end up with is that VB final is equal to VA final plus 5. This is what we have. And it's not a lot of work to come up with this, but now we have a relationship between their final velocities. And of course, this is just one equation and two unknowns, so we need another equation. But like in every collision, we have conservation of momentum. So let's write out that equation as well. So conservation of momentum, conservation of linear momentum. Then this means our initial momentum of the system is equal to the final momentum of the system. And so we have the mass of A times the velocity of A plus mass of B times velocity of B. And the initial condition, which we actually have all of that information, is equal to the mass of A times velocity of A plus mass of B times velocity of B, and the final condition, which we have a relationship between the final velocities that we can plug in to here, right? So we'll end up with one equation, one unknown. It's just a matter of the algebra. So again, careful with the signs. VB initial was negative, right? So we have to be careful of those signs there. But let's go ahead and plug this in. I'll put everything in kilograms. I'll change these masses to kilograms just to standardize it. So mass of A was 0.4 kilograms. Sorry, 0.4. Mass of B was 0.5. And let's plug this in. So we have 0.4 times 2 plus 0.5 times negative 3 is equal to 0.4 VA final plus 0.5 times VB final, but VB final was VA final plus 5. And from here, we end up with negative 0.7 kilogram meters per second is equal to, this comes out to 0.9 VA final plus 2.5 kilogram meters per second. And solving this for VA final, we get VA final is equal to negative 3.56 meters per second. It's the final velocity of A. And so this is based on our coordinate system here. This negative means it's going to be going off to the left. I didn't even bother with assigning directions to it. I mean, I thought that it was probably going to go off to the left, and it did. That makes me feel good that it follows kind of conceptually what we expected. But I didn't even bother with assigning directions to it at first. So VA final is negative 3.56, and VB final, then we can get VB final by plugging back into this relationship here, just adding 5 to VA final. And so we have VB final is equal to negative 3.56 plus 5. And so VB final is equal to 1.44 meters per second. So these are the final velocities after the collision. So it's not like they just bounce back, at the same speed or anything. Just as important to note, it's not like this one just bounced back at 3 and this one just bounced back at 2. The differences in their masses played a role here, as I was alluding to before. Now, if they had the same mass, then they would have just bounced back. This one would have bounced back at 3 and this one would have bounced back at 2, but they didn't have the same mass.